So we are today finishing Dirichet's theorem, okay? And we've reduced Dirichet's theorem down to the following case, right? We want to show that if you have a non-trivial real Dirichlet characters, pi, that L1 pi is not equal to 0. Okay. So yeah, I think I haven't told so many stories in this class. I also have a good story about having been stalked by a student who believed that she was a vampire. But too bad, this is the end of this.
Yeah, it's good.
Not good. It was Indiana University. Yeah. I was stalked by the student. Later it turned out, and later I found out that she believed that she was a vampire. So this was actually before the current vampire case. Okay. So, right, so this is it, right? We broke it down into two cases, right? We did the complex case, and now we're doing the dual case, which is harder. We're going to need two propositions that we mentioned last time, that summation from 1 over n, the summation of the partial sum of the harmonic series is basically log n, right? If we sum from 1 to n, well, it's basically log n plus some constant plus things on the order of 1 over n. Okay. The second proposition that we'll need is another p-series sum estimate, that this is basically 2n to the 1/2 plus some constant plus something on the order of 1 over n to the 1/2. Okay? We're not gonna prove this. Excuse me. Okay, so what we're going to do, so we will, we're going to approximate this thing, L1 chi, with what's called a hyperbolic sum. Okay, so we approximate chi, L1 chi with a hyperbolic sum. Okay, and it goes like this. We let f and n be defined as chi of n over the square root of n times m. Okay. And then we define the hyperbolic sum, s of n, as the sum of these guys, f and n, right, as n and m range over natural numbers whose product is less than or equal to n. Okay. So they are right. They are bounded by some hyperbolic. Right. So if this is the n's and this is the m's, right, then these guys go from here from 1 1 up to 1 n, from here up to 1 n, and then there are these guys in between. So 1. Okay, so you have this chopped off lattice basically. Okay, the lattice is chopped off by the axes and the hyperbole. Okay, so you're going to sum over all those pairs of indices. Okay. And here's the proposition that will finish the theorem, that for, again, chi non-trivial, and a real Dirichlet character, we have, one, that there exists a constant such that s of n is greater than c log n. So this sum is bounded below by log n. Okay. It's growing at a particular rate. 2, s of n is actually 2n to the 1/2 times L1 prime. Okay. It's actually 2n to the 1/2 times L1 prime plus some error as n goes to infinity, plus something on the order of a constant as n goes to infinity. Okay, that is to say that that this we think about the function L1 chi. Right? This is the function L1 chi, right? And what we're saying is that this is basically 1 over 2 root n summation I n over root m n m n less than n. Okay, so we're approximating the L1 chi with this hyperbolic sum. Okay, and what we'll see is that indeed it does approximate it. And further, that the hyperbolic sum grows at a particular rate. Okay. And this is the end. This is the end because by contradiction, we'll say, suppose that L1 chi, suppose you have a non-trivial real character for which L1 chi equals 0, right? Then you have contradiction. Sn then is a constant, is bounded and controlled by a constant. But Sn is growing from below, like log n, right? Sn goes to infinity, contradiction. Okay. So once we finish this theorem, once we finish the proposition, then the theorem is over. Okay, and the course too. We're good. We're good. I only wish that we could go on and on and on. Okay. Okay, so yeah, so this is it, right? This is getting this proposition. We'll finish it up for us. Okay. So we're going to need 2 lemmas to get this to get the proposition. Where should I put them? Gonna need this. I need this thing, so let me move these guys up. Okay, sorry.
I know you said we're not going to prove it. What's the general idea that you prove this to identity? You just copy it out for this?
You just use the integral test, basically. You approximate them by some integral. Yeah, it's simple enough that the reason I'm not doing this is because not because it's hard, but because it's simple. Okay, so here's the first lemma that we're going to need. Let k be some natural number. Then summation I n over the n that are divisors of k is bounded below by 0 for all k, and bounded below by 1 if k is L squared for some. So if k is a square, we know we have a lower bound of 1, and in general we've got a bound of 0. So this thing is always positive, and if k is a square, it's bigger than 1. Okay, and you'll see why we do this when we look at the hyperbolic sum. So the point of the hyperbolic sum, what we're going to do with it is we're going to notice that the sum is over all these indices, right? And we'll see that if we sum over them, if we sum over hyperbola, the point is that if you sum over hyperbola, or if you sum over straight lines going vertically, or you sum over straight lines going horizontally, then you get the same result, right? And each one will give us a different understanding. In analyzing the hyperbolic sum, we'll need to understand this sum. Okay. So here's the proof. Case 1. Say that k is acutely alpha for some prime alpha. Okay. Well, in that case, well, then the divisors are, of course, just powers of p, right? N divides k by n. Well, what are the divisors? The divisors are, of course, 1 and p and p squared, and up to p to the alpha, right? Right, by multiplicativity, you can pull the alphas out, right? Okay, and then you say, okay, well, and what is this? Well, since pi is real, right, since it's a real character, we know that pi p is either -1, 0, or 1. Pi p is -1, 0, or 1. And so we can figure out what this thing is, right? So whatever we get, the thing that we get, this sum, well, if pi p equals 1, then we get alpha plus 1, right? If pi p is -1 and alpha even, and alpha is even, then we get 1, right? If pi p is -1 and alpha is odd, we get 0, right? And if pi p equals 0, we get 1. Okay, so these are the only possibilities, right? And you see that that statement implies that, at least in this case, we have what we wanted, right? Because the sum is always positive, right? It's always bigger than or equal to 0, right? And you see that if it is a square, right? Right? If it's a square, if the alpha is even, right? So like if alpha is even, and then we're going to get 1, right? Something 1 or something bigger than 1. Everyone see that? If this thing, right? If k is something squared, well, there's two possibilities. So it could be this, or it could be this. But in either case, you're going to get you get what we want. Okay. So any questions? Okay. Okay, and then this case 2. In the case of general plane, right? Right. So So K equals some, has some fine factorization, P1, alpha 1 through Pm alpha M, right? In that case, then the divisors of K, well, what are the divisors of K? They're the set of things that look like this, right? P1 beta 1 to Pm beta M, right? Where beta lies between 0 and alpha j, right? For j is 1 through m, right? These are, of course, all divisors, right? Okay, so then you think every divisor, right? Every divisor has m prime powers, right? Has m prime powers. Even though some of them might be ones, right? Some of the exponents might be zeros. Okay, so every divisor has m primes, m powers of primes, right? Some prime to the power, some prime to the power. There'll be m of these guys, right? And everything like this is a divisor. Everything like this is a divisor, where the powers range from 0 to alpha j, right? So then, if you think about this thing, well, then you see that you can write it as a product. As a product like this, right, where the j's range from 1 to n, right? Because if you take, right, if you take this product, what are you going to get? You're going to get things with m prime powers, where the powers range from 0 to alpha j, and you get all such things, right? And so that's the sum. So, and as before, you can only get 0 from this if one of these things is 0, right? If one of these sums is 0, right? But by the previous case, that's going to only happen if alpha is odd, right? We can only get 0. The product equals 0, it can only get one of these factors is 0, right? Some I pj m, right? From m equals 1 to alpha j, 0 alpha j. Is 0, right? But by the previous case, this can only happen if alpha j is on, right? In that case, it's not a square, right? In that case, it's not a square. And so, if you have a square, then you're guaranteed to have 1, or something bigger than 1. Okay. Is that clear? You all seem a little bit off today. You're turned off. I hope that's clear. I think maybe I should have told the story about being a spy. Again, you're all distracted. Okay. So the only, if the thing is a square, you're not going to have any odd powers in it, right? And so you're not going to get 0. So if the thing is a square, you guarantee that this thing is bigger than equal to 1. first lemma. Okay. Okay. The second lemma. Second lemma, again, is a sort of pretty straightforward estimate. Let A be natural numbers and A less than B. Then the sum from n equals A to B of pi n over root n is on the order of A to the negative a half. 2, the sum from A to B of pi n over n is on the order of A to the minus 1. And I'm afraid I'm not gonna prove this. But as I think the proof is not that tricky. So, so now we have all the pieces, and now we can get the proof of the proposition. So this is the end. So. So now let's prove the proposition. Proof of the proposition. First thing we'll get is the bound from below, right? Showing that the thing is bounded below by the logarithm. Okay. So when Sn is bigger than C times log n. So here's the proof. Well, Sn is summation I and root and m as m and n, are in n cross n, and m and this one capital N. Okay. And so we sum along hyperbola. We say, okay, we're going to let k range from 1 to n. We have a k range from 1 to n, and we're going to sum along a hyperbola that are indexed by this k. Okay, so the first hyperbola is just a dot, right? And then you have the rest of them going out to the final nm equals n prime. Okay, so we'll sum along those guys. N, right? And you say, okay, well, let's rewrite this as summation k from 1 to n. Nm equals k. So I'm just going to pull out that factor, which is the root. 1 over root k, summation I n, where nm equals k. That's the same thing as saying that n divide, we're summing over all n that divide k. Right? Because if you know what n is, then you know what m is. Right? These pairs are determined by the first guy, right? Because n will be k over n. Okay, so now you see why we needed that first lemma, right? We wanted to get lower bounds on this guy. Well, we have that this guy, right, is greater than or equal to 1 for k being L squared. right? So we can bound this thing from below, right? This thing is bounded below, from below, by just replace these guys by 1s whenever k is L squared, right? And k, that L squared has to be less than n. Right, or L has to be less than the square root of n, right? And there's something over that. Right? We're gonna okay with that? Okay. Good, right? And then we just rewrite this, right? We're summing over the L's that are less than n, and the square root of n, and we just write it in terms of k, in terms of L, right? Whatever L, right? And now we use the bound on the harmonic series that we got before, right? This thing equals log n to the 1/2 plus something on the order of a constant, right? Something on the order, it's a constant plus something of the size of 1/n, so these two together are the size of a constant. Okay. Right. So we are done, right? We've got the lower bound. This hyperbolic sum is bounded, grows, at least like the log. Okay. So the last thing we're going to do is show that this hyperbolic sum actually is 2 square roots of n times L1 chi plus some error. Okay. And with that, the contradiction will be finished. Okay, so part 2, right, we want to show that Sn actually equals 2 n square roots L1 prime plus some the order of 1 as n goes to infinity. So we consider, of course, Sn. Sn is this thing. Okay, and then what we do is we break the indices into three regions. Okay, so we break this set of indices into 3 regions. The first region is n squared, such that m lies between 1 and root n, and n lies between root n and n over n. The second region, I'll write them down and then I'll explain what they are. I guess you can see what they are. You have your book. Again, n lies between 1 and root n, and so does n. n squared, such that n lies between 1 and root n, and m goes from 1 to root n. No. Goes from root n to n over n. Okay, so the picture is, right, you have here m equals n hyperbola here, right? And the first one is you let m range from 1 to root n, right? And n range from root n upwards. Okay. So it's what's that? This point should be on the hyperbolic. So it's this region here. Right? Okay, so that's region 1, right? Region 3 is similar, right? N ranges from 1 to root n, and M ranges from root n upwards. Right? So this is region 3, and this is of course region 2. So we will we're going to break this sum into into the sums over 1, 2, and 3. Right? Okay. So let's deal with S, the first sum first. So this is the sum of pi n, where n goes from 1 to root n, and n goes from root n to n. Okay. So we'll sum vertically. That is, we're going to take the m's and let them go one by one, right? So we'll let m, we'll fix the m's and sum over the n's, right? Something like this, right? We fix the m's, sum over the n's, right? We can pull the m out because that m is constant. Right? Pulling them out since that sum is constant. And now we see we have something that we know about, right? This is the second lemma, right? The sum of the characteristic function, the sum of the character over square root of n between these two values. Right? And so we have an estimate for that, right? It's on the order of right, it's on the order of, wait a second. Oh, no, that's it. Right, so that this thing is on the order of root n to the minus, this thing is on the order of root n to the minus half, right, by number 1. Right, because we're summing from root n upwards. Okay. Okay, so this thing is in the order of n to the minus 4. Right? Okay. And then let's consider this term. Well, this term is the second P series, right? We have the harmonic series and then we have this other series, right? We have estimates on that guy, right? We know that that this thing is basically 2n to the 4th plus some constant, plus something on the order of n to the negative 4th, right? By this, right? Because we're summing up to n, right? We're summing up. We have to use the top term, right? Is root n. So we have that term to the half, right, plus some constant, plus 1 over the term to the half. Right? Okay, so altogether, right, we see that this thing is like this, right? That S1 has this sort of control line, right? Oops. It's like, no. Okay, right? Right? Which is on the order of constant. Right? Because the negative fourth, the constant, over n to the negative fourth, this is even faster than that. Right? Okay, so the whole thing is on the order of a constant. Okay, so the first part, we don't have to worry about. Okay. Right? So that S1 becomes part of this constant. Okay. And so now we have to deal with S2 and S3 and see where the L function turns up. Everyone all right? Right? All we did was, look at this thing. We summed vertically, and then we used these estimates to see that sum is actually, controlled by a constant. Okay. Okay, 10 more minutes. Good? I don't know. But the other two terms we're gonna sum horizontally. So we're gonna take both of those terms together, S2 and S3. Okay. Well, that would be the sum, and we're gonna sum horizontally. So we fix the n, right? And so we're gonna pull out the terms related to n, right? And sum over the m's here. Okay. So we're summing over this region, right? This full region here. Right? So n ranges from 1 to root n, and the m's go the full range. Okay. Well, again, we have this. We use the p-series estimate, right? We use the p-series estimate that we have here, right? We say, okay, this thing is basically 2 n over m to the half plus some constant plus something on the order of m. What am I making? This should be an n. N over m. N over n, capital N to the half. Sorry, was it? Right? And just by this thing. Right? Okay, so we get summation 1 from n to n. Right? And so let's break it into pieces. Right? We get 2n to the half summation chi n n to the half. No, chi n n, right? Because we have n to the half and n to the half. Right? So we're going to take each of these terms and multiply them by the sum. Okay? So in the first sum, we get 2 capital N to the half times summation. We get this thing, right? And then we get a constant times this thing, n to the half now. Right? And then we get right, then we get something O 1 over n to the half summation 1 this, right? If you, right, right? Because when you multiply this thing by this thing, right, then the n to the 1/2s cancel off, right? You have the n to the half, that's this thing, capital N to the half, that's this thing, right? And so you're left with summation of chi, but chi is controlled by 1, right? Size of chi is controlled by 1. Okay. So everyone all right with that? We're almost there. Okay. Okay. And in the book, we want A, B, and C, right? You start to see where the Dirichlet L function shows up, right? This is part of the Dirichlet, this is part of L1 chi, right? This is part of L1 chi. So, okay, so, right, call L1 chi is, right, the sum of these guys from 1 to infinity, right? So if we look at this thing, this is L1 chi minus the tail term, right? So this thing, 1n/1/2 is L1 chi, but subtracting off the tail, right, where L exceeds 10⁻⁵. Right, of course. Right. And you know that we have some control. Right? This is one of those things that we have control over in the lemma. Right? This is control. This is on the order of n to the -1/2. Right? 1 over the lower index, the lower bound. Okay. So if we look at A, sorry, this is starting to get into bad board work. But if we look at A, right, A is n to the 1/2 times that thing, right? Times that thing which is L1 chi plus something order n to the -1/2. Right? Right? And so we get this thing, which is 2n to the 1/2 L1 plus something on the order of 1. Okay, so that's good, right? We got what we wanted, the 2n to the 1/2 L1 chi plus a half, and then we have these things. We have B and C to worry about, right? We have to show that B and C are also on the order of constants. Well, C is clearly on the order of a constant, right? It's a sum of 1 up to n to the half divided by n to the half, right? So that's constant, right? So the only thing we have to do is worry about B, right? So what about B? What about B? Again, we just use the lemma. Okay? B falls with the lemma here, right? It says that if you're looking at a sum chi n over n, the square root of n, it's on the order of the lower thing to the 1/2. But the lower thing is 1, right? So so this thing is also by lemma. B is on the order of a to the -1/2, where a is 1. So that's also constant. And so that is the end. Goodbye. Okay. So we see that, and this is really, really incredible, right? That you can take the Dirichlet L function, and then this is the really clever part. Realize it as a hyperbolic sum, right? Realize the hyperbolic sum, and then see where the and then get the bound line. So that is one of the great masterpieces of number theory, using the powerful tool of harmonic analysis. Right? So I hope this course and this result and this course in general show you how harmonic analysis really deepens your understanding of what a powerful tool harmonic analysis is. Fourier analysis. Fourier analysis. And eventually harmonic analysis. That's it. Thanks. What?